Here are four scenarios in which an object is moving in a horizontal circular motion. First, we have a funnel here with, say, a ball rolling around on the inside of the funnel, following that blue circular path. The blue X is the center of the circular path. Here we have a conical pendulum. That's a ball on a string being swung in a circular path like this. Not a vertical circle, but this horizontal circle. So the plane of the circle is parallel to the plane of the ground, and the string traces out kind of a cone shape over the course of one full revolution. Up here, we've got a car driving out of the page and making a left-hand turn. So driving out of the page and turning left. So the center of the circular arc it's moving along would be over here to the driver's left. And down here, similarly, we've got a record player with a record spinning and a little bug sitting there on the edge of it, riding along with the spinning record. So the center of its circle would be that blue X right there. In these two cases, we've got static friction acting like serving the function of traction, helping keep the object on that circular path. So I want to look at the free body diagrams in all four of these cases and compare them. First, with our banked curve here, we've got force of gravity pulling down on that marble, let's say, as it rolls around the inside neck of that funnel. But the normal force exerted on the ball by the wall, that will of course be perpendicular to the surface itself. And since the surface is tilted, our normal force will be coming out at a right angle to that. So there's our normal force. And if the ball is just rolling around in this horizontal circle and not accelerating up or down, then we know that our normal force could be broken into components like that. Say a vertical component that must balance out the force of gravity, leaving this inward radial component, the component of the normal force pointing in the negative radial direction in towards the center of our circle. That's providing our centripetal acceleration. Similarly, with the conical pendulum, our tension can be broken up into vertical and horizontal components. The vertical component is balancing gravity since our ball is not accelerating in the vertical direction. And then this radial component, this inward radial component of tension pulling the ball in towards the center of the circle in the negative radial direction, that centripetal force right there is providing our centripetal acceleration, causing the ball to turn. Now, these two FBDs look a little bit different. They've got three forces instead of just the two, but I want you to notice how the normal force and force of friction, which could just be considered the vertical and horizontal components of a single contact force with the ground. That is, these could be the two components. And if we add them with parallelogram method, we would get a total contact force, Fc, from the grounds there, that looks quite like this force of tension or this normal force here. So we got the force of gravity and this total contact force right there. So really, this FBD is identical to these two. We'd have the same thing here with our bug on the disc, on the spinning disc. That force of static friction, that's an interaction with the surface. Normal force, that's an interaction with the surface. These could be considered the two components of a single contact force with the surface. Friction is the component of that contact force parallel to the surface, and normal force is the component of that contact force perpendicular to the surface. So actually we have the same FBD in all of these cases, the force of gravity and a diagonal force. And the vertical component of that diagonal force, in this case Fn, that's balancing the force of gravity. And then the component of that force in the radial direction, in this case the force of static friction and the force of static friction, that radial component, that inward radial component in the negative radial direction, in the centripetal direction, that's providing our centripetal force and our centripetal acceleration curving the path of the object. So let's, now that we have our free body diagrams, be explicit about our axes here. Next step, AAA. For the conical pendulum here, I would have our radial direction pointing radially outwards from the center, so to the left from this particular point of view, r hat. Our tangential direction, tangent to the path, tangent to that blue path right there, would be kind of out of the page from this point of view, so I can't really draw that easily. But then the vertical direction here, which we might normally call the y direction if we're looking at projectile motion, for instance. Let's let the vertical direction be the z direction so that our circle lies in the xy plane. So our vertical direction is the z direction, so our k hat unit vector pointing in the plus z direction is like that. So from our side view here, these side views of our circular motion, we have the radial direction and the z direction. I'll do the same thing up here by the car. Let's see, if for our car, we would have the radial direction to the right from this point of view, pointing away from the center of the circle, and then our vertical direction, our z direction, aligned with the normal force and the force of gravity there. So our k hat unit vector. Let's break down the conical pendulum a bit further. We've got our FBD, we've got AAA, we've got tension broken up into components here, although I may need to do a little more geometry. Let's say if I drop a vertical here and indicate that this is angle theta, then we can tell that this angle is congruent to that angle, so this is also theta, and we're ready to set up Newton's second law for our conical pendulum. So setting up N to L in the radial direction, net radial force over the mass gives our radial acceleration, our centripetal acceleration, and we have the radial component of tension, FTR, pointing in our negative radial direction, so minus FTR. And from the trig, we can see that this leg here is given by minus FT sine theta. So that's the magnitude of the tension times sine theta, and I've got an explicit minus sign there showing that it is in the negative radial direction in towards the center. Set that equal to minus v squared over r, and then this becomes the equation that we might rearrange to solve for something of interest. That's just the radial direction. We should also look at our tangential direction out of the page, and then our vertical direction, our z direction, k hat. Well, out of the page, our tangential direction, there are no forces in this picture pulling the ball out of or into the page. No tangential forces at the moment, so no angular acceleration either. So our ball would have a constant speed as it spins around if this was our FBD. Recall that tangential acceleration, this is the thing that changes the speed, speeds you up or slows you down, as opposed to the radial acceleration, our centripetal acceleration, which is responsible for turning you. So in our z direction, we indicate what we've already discussed, that the net force in the z direction is 0 because our vertical component, our z component of the tension, that would be this right here, our z component of the tension is balancing our force of gravity. So that is Ft cosine theta, the magnitude of the tension times cosine theta must be balancing our mg right here. So we conclude this. So that might be handy for us as well. And since we've noted that this is indicating that we are in uniform circular motion, our speed is not increasing or decreasing here, we might also state this additional uniform circular motion condition, that our speed, v, could be related to the circumference of that circle divided by the period t, the time it takes to complete one revolution. Just to be clear, r would be the radius of the circular path right there. So between these three equations, you could solve for whatever it is that you wanted to know about this ball swinging in this conical pendulum-shaped manner. Okay, let's pause there, and next we'll consider these two cases, the car and the bug on the disc.